Hello, Math 109 students. Welcome to section 3.6. Mathematical models, building functions. This section is probably the hardest section of the whole class. It is a fairly high level of mathematics involved here. But let's get into it, and I really like it. It's probably maybe my favorite section, or at least one of them. Some of you might like it. It's interesting. It's applicable to the real world. So let's just get into it. Build and analyze functions. Real world problems often result in mathematical models that involve functions. These functions need to be constructed or built based on the information given. In building functions, we must be able to translate the verbal description into the language of mathematics. We do this by assigning symbols to represent the independent and dependent variables, and then by finding the function or rule that relates these variables. Okay, so first example. It says let P equals xy be a point on the graph of y equals x squared minus 1. So P, the point P, is a point on the graph of this parabola, and we just learned how to do function transformations, so we should know what this function looks like. Okay, so here's the parabola, x squared minus 1. That means it's shifted down 1, so it's something like this. All right, and we have a point P. Okay, P is the point x, y, somewhere on the parabola. It says express the distance d from P to the origin. So here's the origin, and here's the distance from P to the origin, right? The distance from P to the origin is 0, 0, obviously. As a function, it says express the distance d as a function of x. All right, so the distance formula, you remember, is the square root of x2 minus x1 squared plus y2 minus y1 squared. So in this case, it would be the square root of x minus 0 squared plus y minus 0 squared. But it says as a function of x. So that means I can't have y anywhere in my equation. It's just got to be x. I can only express this distance as it relates to an equation with x in it. So here is going to be one of the big tricks to this whole unit. Instead of expressing the point P as the point x, y, we're going to express it as x, and then instead of y, we got to put that y in terms of x. Well, what is y if I want to write y in terms of x? We need to relate y and x somehow. Well, that's actually pretty obvious. I mean, not the first time you do it, but it's pretty obvious after you've done it a few times that if you're somewhere on this parabola, there's an obvious connection between x and y, and it is given by this equation right here. Here is the connection between x and y everywhere on that parabola. So instead of putting y, I can put this, because this is what y is equal to in terms of x. Every y coordinate is the x coordinate squared minus 1. So instead of putting y, I'm going to put x squared minus 1, because that's what y is everywhere on that parabola. Now let me redo my distance formula. D equals the square root of x minus 0 squared plus that x squared minus 1 minus 0 squared. Let me clean this up. So D equals square root of, what's x minus 0? It's just x. So that's just x squared plus, let me do some side work over here. X squared minus 1 minus 0 is just x squared minus 1 squared. So I'm going to go ahead and FOIL that out. X squared minus 1 times x squared minus 1. I'm just cleaning this up a little bit. You don't, this is not actually completely necessary, but I think Math Excel may require this. So let me FOIL this out. So this is going to be x to the 4th minus x squared plus 1. So x to the 4th minus 2x squared plus 1 when I combine those like terms. And now there's more like terms to combine. I got this x squared combined with this minus 2x squared. So the final model is d of x, distance as a function of x, equals the square root of x to the 4th minus x squared plus 1. That the minus x squared came from combining the minus 2x squared with the positive 1x squared right there to get minus 1x squared. So this is the answer to part A. Express the distance p of the origin as a function of x. That is the answer to part A. Let me rewrite that up here. D of x equals the square root of x to the 4th minus x squared. What was it? Wasn't it plus 1? Plus 1. Part B. What is d if x equals 0? Well, that just means I plug 0 in for x. D of 0 equals the square root of 0 to the 4th minus 0 squared plus 1, which is just the square root of 1, which is just 1. And I actually knew that already, right? Because if x is 0, here's the parabola. That's right here. How far is it from here to the origin? Well, it's 1 unit. And it says, what is d if x is 1? That's part C. Just plug in 1. 1 to the 4th minus 1 squared plus 1. That's going to be 1 minus 1 plus 1. This is again the square root of 1, which is again 1. And I kind of knew that already too if I just look at the graph. This is when x is 1. That's also 1 unit away. All right. Part D. What if x is the square root of 2 over 2? Let me go over here and do that. D of the square root of 2 over 2 means I'm plugging the square root of 2 over 2 in for x. The square root of the square root of 2 over 2 squared plus the square root of 2 over 2. I'm sorry, that's to the 4th, isn't it? To the 4th plus the square root of 2 over 2 squared plus 1. And so that's going to be, if I raise that to the 4th power, that's going to be this. It's going to be the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2. That's 2 and that's 2, so that's going to be 4. And 2 to the 4th is also 4. It's 4 over 4 plus 2 over, I'm sorry. 2 to the 4th power on the bottom, 2 to the 4th power 16. It's 4 over 16 plus, that's going to be square root of 2 squared is 2. 2 to the 2nd is 4th plus 1. So that's 1/4 plus 2/4, that's 3/4. 3/4 plus 1 is 4/4, that's the square root of 7/4. Let me pause it. Which is the square root of 7 over 2, which turns out to be around 1.32. That's my answer to part D. Or if I left it, I could leave it like that also. All right, part E. Use a graphing utility to find the function D and round to 2 decimal points. 2 decimal places, find the value of x at which D has a local minimum. So I'm trying to minimize the distance. I'm trying to find what, notice I kind of already know about where it's going to be. This was 1 away. This was 1 away. I noticed a mistake here. That was supposed to be a minus sign right there. Yeah, I did that. I did it correct on B and C. I just didn't do it correct on part D. So that's going to be square root of 1/4 minus 2/4 plus 1, which is the square root of 3/4, which is the square root of 3 over 2, which is about 0.866. So now I kind of know where the minimum distance is going to be. If this is 1 away and this is 1 away, and the square root of 2 over 2, that's somewhere in here, and that was 0.866 away, then somewhere right in here is going to be the minimum distance. That's going to minimize the distance. Now, I don't know exactly where that is, and that's where the calculator is going to come in handy. So I'm typing in my function into my calculator now. The square root of x to the 4th minus x squared plus 1. And I can see that there's a minimum like right here. Right. So it kind of looks like that. So the minimum is right in there. It's the same minimum right there, which is going to be this point here. But all I care about, it says for x greater than or equal to 0. So I'm only looking at this half of the function. So I'm going to look for this one. So going back to my graph, second calc, minimum is option 3. Okay, left bound, that should be fine for the left bound. Right bound, that should be fine for the right bound. And the minimum is 0.707, 0.866, 0.707, 0.866. So this is the minimum. 0.707 is the square root of 2 over 2, and 0.866 is the square root of 3 over 2. So the minimum distance is found right there, which is what it already asked me to find in part C. I'm sorry, in part D. So let me explain this again. Let me express this in words. The minimum distance. Let me try this again, a little bit neater. A minimum distance of 0.866 units is achieved when x is 0.707. So the minimum distance is 0.866, and it occurs when x is 0.707. So this point right here is when x is 0.707, and that makes this distance right here be 0.866. All right, let me reiterate what we did. To express the distance, all right, we used the distance formula. So it says express the distance, but that means we used the distance formula, which was that. But we needed to do it as a function of x only, which means I had to get this point not as an xy point, but I had to make both the x and the y coordinates be in terms of x itself, which means I had to rewrite the y coordinate in terms of x, and I got that from other information in the problem, which was the fact that we're on this parabola means that all the y coordinates were equal to the x squared minus 1 expression. So instead of writing xy, I wrote it as x squared minus 1. Then I did the distance formula. Okay, and so once that was done, the rest of it wasn't really hard. Then it's just a matter of plugging stuff in or putting in your calculator and finding a minimum or a maximum or whatever. But this is, maybe you can see kind of how this could be really useful in the real world. Let's say you had a mountain range here surrounding a village. Let's say you're trying to find the best place to put a water tower on this mountain range that would minimize the distance to get that water to that village. And you just found it. Or if you want, maybe you think more militarily, maybe this is the place where you need to put a base which is closest to your enemy's location or something like that. So lots of different uses here for other applications. Let's say this is some sort of a aerodynamic shape of a car or a plane or something, and here's the battery of the car, and this is where you can put the lights or something to minimize the distance between the power source and what you're trying to power. All right, next example. Okay, we're doing the area of a rectangle. A rectangle has one corner in quadrant 1 on the graph of y equals 25 minus x squared, another at the origin, a third on the positive y-axis, a fourth on the positive x-axis. So let's look at this parabola. What does that parabola look like? If we rewrote that as y equals negative x squared plus 25, maybe you could see that it's a parabola that's shifted up by 25 units and that is flipped to open downward. So it's going to look like this. Here's 25. It's going to look like that. Okay. And we have one corner of our rectangle on this parabola, another corner at the origin. And then so obviously the other corner is going to be on the positive x and the positive y axis. So I've got this rectangle right here. All right. Now, it wants me to express the area as a function of x. What is the area of a rectangle in general? It is length times width. Or you could say, in this case, you could say it's the width times the height. It doesn't matter if you call it length or width or height or whatever. It's one dimension times the other dimension. So if we call this the width, okay, and this the height, and we want to express both of these in terms of x, okay, how far over is this? Let's call that x instead of w, since we need to express it as a function of x. Let's call that x. We go over this far, that's the x. That's x. So in this case, it'll equal x times, and if this is the height, how can I express the height as a function of x? Well, the height is the same thing as y, right? That's the y coordinate of this point. The height is how much we go up here. The width is how much we go over horizontally, that's x. The height is how much we go up, that's y, but I can't put y. I gotta put x. How can I express y in terms of x? Same thing as last time, right? We're using this. All right, so that is y equals that. Everywhere on that parabola, the y coordinate is equal to 25 minus the x coordinate squared. So the y coordinate is equal to 25 minus x squared. So instead of putting y or height, I'm putting 25 minus x squared, because that is the height of that rectangle wherever I am on the parabola. So I can distribute that. That's going to be 25x minus x cubed. Okay. So area as a function of x equals 25 minus x cubed. All right, part B. What is the domain? The domain is the possible values of x. Okay. Well, how far, like, what's the minimum value for this x here, and it still be a rectangle? Well, I can go over to, I can go this way, this way, this way, this way, this way, until I'm here, and it'll be a long tall, skinny rectangle, but I can't go all the way to 0 or it won't be a rectangle anymore. It'll just be a line. So the domain will go from 0, non-inclusive. And how far can I go this way? I can go all the way to here. Once I get to here, I'm no longer a rectangle. I can have a really wide, short rectangle, but once I get to here, I'm no longer a rectangle, I'm a line. So how far is this? What is this point right here? That's as far as I can go with x to satisfy the conditions in this problem, that I would be a rectangle in the first quadrant inside of that parabola. So the way that I find that is I can just find the x coordinate of that, the x-intercept of this parabola by saying 0 equals 25 minus x squared and solve it. So move the 25 over. 25 equals, or just move the x squared over or whatever, and you get 25 equals x squared. And then take the square root and you get x equals plus or minus 5. Well, this is 5, and over here over on the left side I've got negative 5. I don't care about that because I only care about the first quadrant here. So the domain means that x can go from anywhere from 0 to 5 to satisfy the conditions of this problem where this rectangle is located in the first quadrant somewhere inside of this parabola. Part C, graph. I'm going to simply graph this area function in my calculator, and it wants to find the value of x that makes the largest areas to maximize the area. So I'm going to go up here. I'm going to graph my area function, which was 25x minus x squared. And I'm also going to think, or was it x cubed? I think it was x. What was it? It was x cubed. 3. All right, now I'm going to think about my window. You remember on part C, I think it was, it asked me to find the domain. That's a good thing for my window because I already found what my window should be by finding the domain. The x min should be 0. The x max should be 5 because that's my domain. That's the only thing, x has to be from there to there or it wouldn't satisfy the problem. All right, so from 0 to 5. Now let me think about my y. My y in this case, if I'm doing this function, the y value is the area, right? That is the y value. The y is this. So what is the area? The area is the area of this rectangle right here. So I'm just trying to think what should my maximum y value be so that I know that I'm going to have the area of this rectangle be inside of that, be below that. Well, let me think about that. If this was, let's say, 5 and this was 25, that means it would go all the way here. I know that's going to include it. If that was 5 and that was 25, that'd be 125 if I multiply them together. So I know it's going to be less than 125. So I'm going to put my y max, I'm going to put it at 100 and just see. If it's not enough or it's too much, I'll change it. My y min, I can let that be 0. Like that would be the minimum value for the area. Okay, let me go ahead and graph and see what that looks like. And I have this pretty cool looking graph right here where the maximum is found right here at the top of this interesting looking curve. So I'm going to find the maximum by hitting second calc. Option 4. That's good for my left bound. My right bound, I can click to the right until I know I'm to the right of that top of that, the peak of that curve. So that's good for the right bound. Hit enter again. And my maximum is 2.89, 48.11. 2.89, 48.11. Now, it's part D actually asks for what value of x is the area largest. So 2.89 is really the only answer it's looking for. 2.89, it answers the question. To be thorough, I would like to say a maximum area of 48.11 2.11 units squared is achieved by when x is 2.89. That answers the question very thoroughly, but all you have to do to answer the question that it actually asks in Math Excel is just to put that x coordinate right there, because that's all it asks for. Okay, third and final example here. Suppose two planes flying at the same altitude are headed toward each other. One plane is flying due south at a ground speed of 400 miles per hour and is 600 miles from the potential intersection point of the planes. The other plane is flying due west with a ground speed of 250 miles per hour and is 400 miles from the potential intersection point of the planes. All right, let me draw that. Here's one plane. Okay, that's my plane. Just imagine that's the plane. And it is flying due south. Okay, its speed is 400 miles per hour, and it is 600 miles from the potential intersection point, this being the potential intersection point. The other plane is flying due west. So here's my other plane. Here's my other plane, and it's flying due west at what? 250 miles per hour, and it is 400 miles from the potential intersection point. Okay. Build a model that expresses the distance d between the planes. So how far apart are the planes? Here is d. Do you see a shape that we can use to model d? I do. It's a right triangle. I'm going to use, in fact, the Pythagorean Theorem. I'm going to say a squared plus b squared equals c squared, where c is actually d. So if we solve for c, we just take the square root of both sides. So I'm just going to say d equals the square root of a squared plus b squared. In this case, d equals the square root. Let's call this a. What is a? A is 600 miles, but it's not constantly 600 miles. It's not staying 600 miles. It is changing very rapidly. This plane is going 400 miles per hour in this direction. So a minute later, an hour later, it's only 200 miles. An hour later, it's already past it. So it starts out 400. Sorry. It starts out 600, but it's decreasing by 400 miles every hour, which I will call t, the time in hours. So it's 600 miles, but that 600 miles is decreasing by 400 miles every time another hour. Every time another hour passes, so 400 miles times the number of hours, which I'm going to call t. Plus, let's call this b. What is b? Well, b is 400, but again, it's not staying 400. It is decreasing by 250 miles every hour. So it's going to be 400 minus 250 times every hour that passes by, which I'm going to call t. What does this say? It says build a model that expresses the distance d as a function of time t. So that's what I've just done. I'm going to clean it up some. All right, so I'm going to do a little side work here. 600 minus 400t times 600 minus 400t. That's going to be 6 times 6 is 36. 0, 0, 0, 0 minus 24, 0, 0, 0, 0 t minus another 24, 0, 0, 0, 0 t plus 16, 0, 0, 0, 0 t squared. So that's 160,000 t squared minus 480,000 t plus 360,000. All right, that's what I got when I foiled that out. Let me foil this out now. 400 minus 250t times 400 minus 250t. That's going to be 16,000 minus 4 times 25 is 100. And I've got 0, 0, 0 minus another 100, 0, 0, 0 plus let's see. That's 625, 0, 0 t squared. So let's see if I can combine my like terms now. 625, 0, 0 plus 1, 6, 0, 0, 0, 0. So d of t equals the square root of 22,250 t squared. That's when I added that with that. Now that's a 2 there, that's a 2 there. That's minus 200,000 t. So let me add that and that. That's going to be minus 680,000 t. Now add that and that. 360, 0, 0, 0 plus 160, 0, 0, 0 equals. So plus 520, 0, 0, 0. So this is my final answer for part A, which was asking me to build a model. Part B says use a graphing utility and figure out how close those planes come to each other. So what I'm going to do, I'm going to put this in my calculator. All right. So the square root of 222,500 t squared, 222,500 x squared minus 680,000 t 680,000x plus 520,000. Now let me think about my window for this. X is actually time. Time, the minimum value of time would be 0. What do I want my maximum amount of time to be? I want my maximum amount of time to be, let me think about that. Well, how long is it going to take them to get to this intersection roundabout? If this thing is 600 miles away and it's going 400 miles an hour, it's going to be there. It's going to get there in an hour and a half. If this thing is 400 miles away and it's going 250 miles an hour, that means it's about 1 3/4 hours. So, so this is going to be, I know 2 hours would be long enough. I'm going to try let's try like 1.8. I don't want to get too high. The X scale, 1's fine for that. The Y minimum, the Y is actually the distance. Well, what's the maximum distance away that they would be? The minimum distance away they would be 0. Right? That's if they that's the minimum that's the minimum distance they could be apart would be 0. That would be if they actually hit one another. The maximum distance, well, they're right here. They're going to be this 600, that's 400. So I don't know exactly what this distance is. I could figure it out, but it's not much more than 600. It's going to be something like 650 or 700, something like that. And I know that they're going to be closer than that. So I'm going to put something like 650 right here and see what happens. All right. And here's our graph. Look at this graph. So if we follow the blue line here, they're getting closer, getting closer, getting closer, getting closer. And they get right, that's as close as they get to one another right there. And then they're getting farther and farther away. So at that moment right there, that's when they got the closest. So if I want to find what time that was and how close they were, I hit second calc, minimum. That's good enough for the left bound. Now let me click to the right until I get to the right of that point. Keep on going, keep on going, keep on going. That's good enough right there. Enter again, and it tells me that the minimum is 1.53, 21.2 basically. 1.53, 21.2. So part B asks me, how close do the planes come to each other? What will the answer be? 21.2 miles is what the answer to that would be. Then it says, at what time are the planes closest? We would say 1.53 hours after they have started. After the problem begins, it's 1.53 hours until they are closest. And that answers the question. Those are all the examples I have for this section. I know this section is going to be probably a little tough on you. Hopefully these examples will help you vary a whole lot with some of the homework problems. That some of those homework problems are just like these examples. But do the best you can on it. And I'll see you again when we finish our test. A practice test is available for you. The test will be a lot like the practice test, so use that practice test to review and to prepare yourself. When you feel good about the practice test is when you should feel good about being ready to take the test. So good luck on finishing this assignment, and good luck on your practice test, and especially good luck on your test coming up.